Today we're going to discuss an amazing mathematical theorem associated with group theory. It's called the fundamental theorem of finite abelian groups. The theorem essentially allows us to take abelian groups, which are commutative groups, and break them down into very simple components. The fundamental theorem of finite abelian groups essentially states that all abelian groups, which is basically all groups that have the commutative property, can be broken down into the direct sum of cyclic groups. Now at the moment you may not know what a direct sum is, but it's a very broad component of mathematics, and I'll explain it shortly. In order for us to understand the topic for today, we have to go into and explain the direct sum. The direct sum, typically denoted with a plus sign with a circle around it, is an operation that appears in many branches of mathematics ranging from matrices to group theory, and it has a common theme everywhere it's used, but the specific implementation can be a little bit different from one instance to the next. So in group theory, it allows us to take smaller groups and construct larger groups. If we take C2 direct sum C3, then we get all ordered pairs where the first coordinate is from C2 and the second coordinate is from C3. The group operation is then carried out component-wise. So you may hear mathematicians say there are only two abelian groups of order 4 up to isomorphism. They are the cyclic group of order 4 and the Klein 4 group. So how do mathematicians know that? Well, the topic that we're discussing today, through the use of direct sums and the decomposition of the abelian groups into direct sums, will allow us to figure out how mathematicians know that fact. The fundamental theorem of finite abelian groups states that all abelian groups, which is what we know as groups that have the commutative property, can be decomposed into much similar structures using the direct sum composition. These individual building blocks are called the cyclic groups, and we've already studied those. So recall that cyclic groups, a cyclic group of order n, is isomorphic to the integers modulo n. Cyclic groups are easy to represent in mathematics, and they're also easy to encode in computer code. So that means the direct sum components, called summands, are always going to be cyclic groups, which means that we could appeal to their isomorphic nature of the integers modulo n to allow us to create very simple implementations of representing abelian groups as cyclic groups using direct sums. To determine the structure of a finite abelian group, we simply factor its order. So for example, if the order of the abelian group we're trying to analyze is 360, then we simply write the value 360 in its prime factor form as 2 to the third times 3 squared times 5. This prime factorization reveals how the abelian group can be decomposed into its cyclic summand components. Each summand of the direct sum corresponds to a prime base. The exponent of that prime base tells us how many cyclic factors of that prime are available. As a result, it gives us a counting method for determining how many abelian groups of a certain order exist, up to isomorphism to be clear. To build on what I said earlier, once we have the prime powers, or a prime base raised to an exponent, we can partition that exponent to form the different potential cyclic groups associated with that prime base. So for example, if we had 2 cubed, which would represent an abelian group of order 8, that exponent could be represented as 1 plus 1 plus 1, or 1 plus 2, or just simply 3. So this would correspond to the 3 potential non-isomorphic abelian groups of order 8. It would be C8, or C2 direct sum C4, or C2 direct sum C2 direct sum C2, or what we might say 3 copies of C2. Each of these represent 3 non-isomorphic direct sum decompositions of abelian groups of order 8. So there are only 3 groups that are abelian that have order 8. Now let's be very clear and forthcoming. It's very unlikely that you will completely follow this discussion without some worked out examples. So let me take a moment to head over to my notebook, and I will demonstrate how we can take an abelian group of a given order and decompose it into its direct sum components. More to the point, for a given order, we'll be able to calculate how many abelian groups there are for that given order. In order to understand this conversation that we're having, we need to define what it means to have a direct sum. So it's not a complicated construction. but it does appear in several places in mathematics. And even though we call it the direct sum, the specific implementations may differ depending on the structure, but there is a common notion about what it does. So let's discuss what a direct sum looks like inside of group theory. So let me go ahead and represent this using cyclic groups. So let's suppose that I'm going to say C2 and I want to do direct sum C3. Okay? Now, what do we know C2 is isomorphic to? Well, we know that C2 is isomorphic to the integers mod 2. And we know that C3 is isomorphic to the integers mod 3. So as was typical, I'm saying cyclic groups, but let's go ahead and use the modular arithmetic value group to represent what we're talking about. So actually the construction I'm going to be giving is going to be Z2 direct sum Z3. Okay, so now notice that the elements in Z2 are 0 and 1, and notice that the elements in Z3 would be 0, 1, and 2. So all the components that are inside the direct sum look like this. It will be 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, and then 1, 2. Now here's what I want you guys to see. This is essentially all combinations of elements from C2 as the first coordinate, or Z2 rather, and then notice that on the second coordinate, these are all the combinations that are coming from Z3. So every possible combination from Z2 as the first coordinate and Z3 as the second coordinate are present. Okay, now how do we do this? Well, let's suppose that we want to take something like 1, 1, and I want to add it to, let's suppose, 0, 2. All right. Well, what we do is we do the operation component-wise. I'm going to add these two components, but the operation will follow Z mod 2. And then I will add these two components, except this operation will come from Z mod 3. Okay, so the result will be 1 plus 0, 1 plus 2. So notice that we took the first coordinate and the first coordinate and we added them here. And we took this second coordinate and the second coordinate and we're adding them here. So the result will be 1 plus 0, which is 1, mod 2, and 1 plus 2, which is 3, mod 3, so we have 0. Okay, well, let's see what happens if we take the element 1, 2, and we add it to itself, 1, 2. Let's see what happens. Well, this would be 1 plus 1, 2 plus 2. Well, 1 plus 1 is 2, but in mod 2, this becomes 0. And 2 plus 2 would be 4, but in mod 3, that becomes 1. So what happens is any time that you take the direct sum of two groups, the result will also be a group. So you kind of get that automatically. Now that's very strong. That means you don't have to go through a lot of exhaustive checking. If you start out with a group and another group, and you write their direct sum, or you compose their direct sum, that means you automatically have another group. And so that takes all the checking out of it, but you end up with a group that's kind of fascinating in a way. So here's what I recommend. I'm going to go to a new page, and I'm actually going to write out the Cayley table for this entire group. So it's going to take just a bit, but I believe that we'll be able to work through it. So we're going to do 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, and 1, 2. And then I'm going to create my, that's my left operand label. Now I'm going to create my right operand label. So it's going to be 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, and 1 comma 2. Okay, I'm going to draw my grid out here. Okay, now it turns out that whenever you have the identity, comma the identity, you get the identity element. So this element right here, 0, comma 0, is going to end up being the identity. So the operation table is going to basically look like this. And by the way, what do we call the operation table for a group? The Cayley table. Okay, that was pretty simple. And remember, anytime we're taking the direct sum of cyclic groups, that means that that's how we decompose abelian groups. So if we take the direct sum of cyclic groups, or in this case, a cyclic groups isomorphic, the modular arithmetic groups, that means that we're going to have an abelian group. That means we have the commutative property. So that means this table gets a lot easier to fill out because every row becomes the column as well. So we just go down this way with the values that we've already created. Okay, so now let's go through here. 0, comma 1 plus 0, comma 1, that becomes 0, comma 2. And here, this will become 0, comma 0 because 0 plus 0 is 0, but 1 plus 2 in mod 3 becomes 0. So this is 0, comma 0. And now we have, looks like 1, comma 1. Okay. And then we have 1, comma 2. And then 1, comma 0. And again, once we have a row, we also have a column, so it'll be 0, 1, 0, 2. Then we have 0, 0, 1, comma 1, 1, comma 2, and then 1, comma 0. All right, now we take off this row. 0, 2 plus 0, 2 would be 0, comma 4, but 4 mod 3 becomes 1. Now we have 1, comma 2. As you guys can see, this could be very arithmetic error prone, so just be careful when you're filling out these Cayley tables for direct sums. This is a very simple group too, so maybe we might even want to have a computer help us, but I'm doing this manually just so we can see the calculations and you can work along with me. So 0, comma 2, and then we have 1, comma 1, so that becomes 1, comma 0. 1 plus 0 is 1, but 1 plus 2 mod 3 becomes 0. And then we have 0, 2, and then 1, 2, so that becomes 1, comma 1. Okay, so we got 0, 2, 0, 0, 0, 1. Then we have 1, 2, 1, 0, and 1, 1. Okay, now 1, comma 0 plus 1, comma 0, that becomes 0, comma 0, because 1 plus 1 mod 2 is 0, 0 plus 0 mod 3 is 0. Good. Then we have 0, comma 1 over here, and we have 0, comma 2. So 0, 1, and 0, 2. Okay, so we're getting there. So this becomes 0, comma 2, and then this will be 0, comma 0. And so we have 0, comma 0 here, and then what is 1 plus 1 is 0, and then 2 plus 2 is 4 mod 3 becomes 1. Now a quick check, in a Cayley table, every row and every column will have every element appearing exactly once. That's always a property of a group. In a Cayley table, every element will appear exactly once. So this is kind of interesting, and I hope you guys remember that when we were saying, whenever we have an isomorphic mapping, we always can determine that generators map to generators and identities map to identities. So what I'm going to tell you, and I'll explain how I know this later, C2 direct sum C3 is actually isomorphic to C6. Now this is a unique property, so anytime that you have an order of 6 or something where all the prime factors are raised to 1, that means you just multiply the summands and you can get the cyclic group of just itself without the decomposition. Well, you may say, wow, that's kind of interesting. So how can we derive that? Like, how do we know this is a cyclic group? How do we know that this is going to be what we think it is? Well, remember the isomorphic mapping. So I've said generators map to generators. So what is the generator in both groups? It would be the number 1. So that means that 1 comma 1 is going to be a generator for this group. And what's a generator of this one? Well, just the number 1. So if we map these two together, then that means I can go through and I can just generate them to get all the elements on both sides. So what is 1 plus 1? Well, that becomes 2 over here, but what is 1 plus 1 over here? That becomes 0, comma 2. Okay, well, add 1 to this, you get 3. Add 1 comma 1 to this, you get 1 comma 0. Because 1 plus 0 is 1, 1 plus 2 is 3, mod 3 is 0. So we add 1 more to 3, we get 4, because I'm using the generator over here, I'm using the generator over here. So what is 1 plus 0 plus 1 plus 1? That would be 0, comma 1. Now we go over here and say, what is 4 plus 1? We get 5. Add 1 comma 1 to this one, we get 1 comma 2. And then finally, we have, what is 1 plus 1? That is 6, but what is 6 in Z mod 6? Because it'd be the same thing we do the isomorphic mapping. We get the identity element, which is 0. So we label this sometimes with the E. This is the identity element. And by the way, in a direct sum, the identity, comma, the identity of this individual group components will be the identity in the direct sum. So hopefully I get 0, comma 0 out of this. So when I take 1, comma 2 and add 1, comma 1, 1 plus 1 mod 2 is 0. 1 plus 2 mod 3 is 0, and you see that I actually have the identity. And since this element by itself generates the entire group of elements, and this is a direct sum, we know that there's a homomorphic mapping that I just used for the generator. So all I did was just take the generator, because in an isomorphic mapping, generators map to generators. So since this group is generated by one element, it must be cyclic. All cyclic groups of a given order are isomorphic. So combining all that together, we know that C2 direct sum C3 must be isomorphic to C6. So isn't that kind of a neat property? I mean, it's just amazing and how, and sometimes I get fascinated with all these different ways that mathematical properties hold true no matter which vantage point that you look at it. Okay, so I think now I've demonstrated what a direct sum is and how sometimes direct sums can actually be represented as something simple. So C6, that's pretty simple. C2 direct sum C3, it's not necessarily difficult, but it's certainly easier to represent it as C6. So deriving this isomorphism, how many abelian groups of order 6 are there? Well, how many abelian groups of order 6 are there? It turns out that there is just one. Now there's other groups of order 6, like the symmetric group S3, but for abelian groups, there's exactly one group of order 6 that is abelian, up to isomorphism. Never forget to say that. Okay, and it's common for mathematicians to sometimes say that when they're talking to each other, because they assume that in the abstract nature of what they're discussing, up to isomorphism is sometimes implied, but it's always best to state it no matter what the arena is or the audience. Okay, so now let's go and start a new page, and I want to show you how you can actually calculate how many abelian groups of a given order there are. So let's talk about abelian groups of order 4. So abelian groups of order 4. What we do is we take the number 4 and we write it in prime factored form. So this is 2 squared. It's a relatively simple thing. So when you break the number down into its prime factored form, you then look at the individual prime bases, which will be a prime power, and then you take their exponent, 2, and then break it off into integer partitions. Integer partitions basically means all the ways that you could take natural numbers to sum up to some value. So now this is a little bit confusing because the prime base is 2 and the exponent is 2. So right now we're talking about the exponent. This is the exponent 2. So how many ways are there to sum up natural numbers to 2? Well, we have 1 plus 1, and we just have the number 2. So since that's the two integer partitions of the exponent, that means that we could take the number 2 and write it as 1 plus 1, which gives us, and breaking it apart, kind of using the properties of exponents, this is 2 times 2, which implies that we have one abelian group C2 direct sum C2. Or we could use the integer partition of just 2, which means that we have C2 squared, but we want to simplify that as just C4. So how many abelian groups of order 4 are there? Up to isomorphism, there are 2. We have the first one and we have the second one. And it turns out that this one right here has a very special name in mathematics. We refer to it as the Klein 4 group. It's the Klein 4 group. The Klein 4 group is the same mathematician, the name Klein, it's the same mathematician, if you were to Google it, the Klein bottle. It's that kind of abstract, kind of multi-dimensional bottle where it kind of loops in, passes through itself. Really kind of strange. It's very neat because I've seen blown glass representations of it, and it's really cool. But it's the same mathematician Klein. Okay, so this one example, relatively simple. But if we're not careful, we may see patterns that may not exist in general. So let's now consider something else. What about the abelian groups of order 8? Okay, so abelian groups of order 8. Well, we take the number 8 and we represent it in prime factor form, which is 2 to the third. Okay, now what we do is we take that exponent, 3, and we see how many ways that we can create an integer partition. Well, the first partition is relatively easy. It's just the number 3. The second partition would be to do 1 plus 2. And then finally, we could do 1 plus 1 plus 1. Now, I don't know if you're familiar with this. This is kind of related to the coin change problem. Suppose someone goes to a register and they get 60 cents in change. How many different ways are there for someone to give back 60 cents using penny, dimes, nickels, quarters? Well, that's actually called the coin change problem, and it's kind of a famous computer science problem that uses recursions, because all you have to do is just kind of subtract one off, and then the remaining you calculate the partitions of that value. So I'll leave that for you guys to figure out another day. Let me rehash. We take the order of the group. How many abelian groups of order 8? We take the order. We represent it in prime factored form. We then take the exponent and represent that exponent as all possible integer partitions. In this case, we can integer partitions are all the ways that you could sum the number up using natural numbers, which are the numbers 1, 2, 3, etc. So we can just take the number 3. That's easy. 1 plus 2, easy. And then 1 plus 1. Now, to help yourself keep things straight, you always want your sum to always be increasing with numbers, because technically I guess you could write 2 plus 1. But up to commutativity, we say these are going to be the same. So how many abelian groups of order 8 are there? Well, we only have one prime base. Its exponent is 3. There's 3 ways to write integer partitions. There's 3 ways. There's 3 integer partitions of the number 3. And so that means the groups of order 8 are C2 to the third, which becomes C8. We have C2 to the first, direct sum C2 squared. To simplify this, you get C2 direct sum C4. And then finally, you have C2 to the first, direct sum C2 to the first, direct sum C2 to the first. And this just becomes C2 direct sum C2 direct sum C2. Now, we can write this kind of shorthand notation. If you guys are familiar with like the series summation, you can actually do this. Since there's 3 copies of the same one, you could write I equals 1 to 3 of C2. So that helps whenever things get really big. It's a little bit wasteful here. It's not that big of a deal. But it's important that we look at what may fall out of this. So take a look at this one. Notice that the bottom one has a C2 component kind of all spanned out. So C2 direct sum C2 direct sum C2, this is where things could be a little bit confusing, because technically this could be C2 direct sum the Klein 4 group. And the reason for that is technically the direct sum is actually a binary operator, which means you can only take them 2 at a time, and we say it's left associative. So really what this is we could draw the parentheses around this to do this first and then do that. So in this case, it would be the Klein 4 group direct sum C2. Now, the direct sums are, if you were to actually do this, you would find that you would compute the direct sum, and then you'd have all those parentheses, and then you would do a direct sum of C2. And so technically, the left coordinate of this broader direct sum would be the direct sum of the Klein 4 group. All that gets a little bit confusing. So just to kind of save yourself some sanity, imagine that you just have an ordered triple here, where the first coordinate is C2, the second coordinate is C2, and the third coordinate is from C2, okay? So what I recommend is that for now, let's not get too bogged down into things, and let's just keep things kind of simple. And I'll erase this just so we can get the mess out of the way. So this was C2 to the first, direct sum, C2 to the first, direct sum, C2 to the first. Okay. Great. So for now, don't worry about associating them, other than just remember, when you have the direct sum, you can associate them in any order you want to. So C2 direct sum C2, I could put parentheses there, or I could do C2 direct sum C2. The operands also commute. So if you have like C2 direct sum the Klein 4 group, that would be isomorphic to the Klein 4 group direct sum C2. So the direct sum is both commutative and it is associative up to isomorphism. So you see how we're kind of like nesting these things and kind of building up complex structures? Okay, great. Well, let me go to a new page and let's try to see if we can complicate this a little bit more, because for right now I've only been using powers of a prime as the orders. So let's suppose we take an order to where we say a billion groups of order 2 to the third times 3 squared times 5. Okay, so what is that value? That's 8 times 5, which is 40, times 9, which is 360. Okay, so we have 2 to the third times 3 squared times 5, and we get 360. Okay, so the question is, how many abelian groups of order 360, and obviously up to isomorphism? Okay, so what we need to do is we need to take the number 360 and break it apart into its prime factored form, which we already have. So what we're going to do now is we're going to take each one of these prime bases, and notice that we have 3 as the exponent. And we have to separate this into its integer partitions. So we've already kind of done it. So we have 3, and then we have 1 plus 2, and then we have 1 plus 1, plus 1. Then we have 3 squared. So we take that exponent 2 and figure out all the integer partitions of the 2. We have 2, and then we have 1 plus 1. And then we have 5, which is implied to be what? 5 to the first? That one's kind of easy. So 5 to the first, the number 1 only has one integer partition, and that's just 1. Okay, so what we're going to say is we have 3 abelian groups of order 8. We have 2 abelian groups of order 9, and we have 1 abelian group of order 5. So we have 3 abelian groups of order 8. We have 2 abelian groups of order 9. And we have 1 abelian group of order 5. Okay, so let's write these out. We've already kind of done these already. So we have effectively C8. We have C2 direct sum C4. And then we have C2 direct sum C2 direct sum C2. So all of these are the component for the prime base 2. So we have 3 of them. Here, let's go through and I'll kind of jump to it. We have C9, which comes from the 3 squared, and then we have C3 direct sum C3. And then down here we just have C5. So notice that we have 3 here, we have 2 here, and we have 1. And so the number of abelian groups of order 360, sorry about that, the number of abelian groups of order 360 is 3 times 2 times 1, which is 6. There are 6 abelian groups of order 360. Okay, well, what are they? Well, you basically just take each one of these and iterate through them all. So I'll go ahead and say this. We have C8 direct sum, C9 direct sum, C5. That's one of them. Now, there's only one on this right component, so it's going to be C8 direct sum, C3 direct sum, C3. Then we're going to have well, we've already run through all these other ones, so the next one will be what? C2 direct sum, C4, C2 direct sum, C4, direct sum, C9, direct sum, C5. So we have C2, direct sum, C4, direct sum, not C9, but now we have C3, direct sum, C3, direct sum, C5. So this would be kind of a complicated group to write out, right? And then we're going to iterate through the last set of the 2's here. We're going to have C2, gosh, this is a lot, C2, direct sum, C2, direct sum, C2, direct sum, C9, direct sum, C5. C2, direct sum, C2, direct sum, C2, direct sum, C3, direct sum, C3, direct sum, C5. And notice that we have 1, 2, 3, 4, 5, 6. Okay, so what I want you guys to imagine is that each one of these kind of represents, now I'm not trying to draw any kind of isomorphic mapping here. I'll even use a different symbol so that way we don't get confused. Notice that if I was to label these up here as I got 1, 2, and then 3, and this is 1 and 2, and this is just 1. Notice that what I'm doing is effectively this, where I have 1, 1, 1, where this is the first one of order 8, the first one of order 9, and the first one of order 5. And then basically, since the 5 doesn't iterate, it's going to be the first one of the base 2, and it's going to be the second one for the base 3, and then we have 1 again. And then we iterate to where we're going to have now the second one, 1, 1, and then we're going to have 2, 2, 1, and then finally we have 3, 1, 1, and then 3, 2, 1. So why does this last coordinate always say the same? These are just a numbering mechanism. You don't have, these are nothing related to groups, these things that I've drawn with these brackets. All we're saying is that this 1 that stays the same at each one of these, like it doesn't change at all, that's only because there's only one C5. The abelian group of order 5, there's only one of those. But for the abelian group of order 9, there's 2 of those, so in each one of these we keep iterating between this one and this one. So notice here, for the C, so I'll underline the blue ones. So this is the prime base 2, 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 and prime base 2. Okay, and then the green will be prime base 9, prime base 9. Oh, look at what I did. I actually made a little mistake here. This should be direct sum C5. I actually left that off. Sorry about that. This is prime base 9, prime base 9, prime base 9, prime base 9. And then finally, we have C5, 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 and C5. So all of these things over here is just basically trying to give a little bit of a numbering to these things, but this is actually, if it's not helpful, then just disregard it. Hopefully you understand where I'm coming from. So how many abelian groups of order 360 are there up to isomorphism? Well, we calculate. There are exactly 6, and specifically we can create those using this construction here. Let me take a moment to summarize what we discussed. Every finite abelian group is isomorphic to a direct sum of cyclic groups. We derive the summands from the prime power factors. We can calculate how many abelian groups there are for a given order. Prime factorization and integer partitions allow us to determine that structure and the number of such structures. Thank you for watching this lecture video. I hope it was helpful. I hope it was insightful. Please, if you have any comments, let me know what I did right. Let me know what I can improve on. I do read those comments to help me create better lecture videos in the future. So until next lecture, see you guys.